Hi, and welcome back. Today we're going to cover sections 7.1 and 7.2 because these two sections really go hand in hand. So we're going to talk about rational functions and simplifying rational expressions, as well as multiplying and dividing rational expressions. Let's jump right in. So the first thing to note about a rational expression is that it sounds really fancy, but what we're talking about are fractions. Fractions are friends. All right, now that being said, let's jump into our first example. That is a 5. I'll make sure that looks like a 5. There we go. Now, the first thing that you really need to understand about fractions is that you cannot divide by 0. We've discussed this before. However, that also means, especially with rational expressions, you might have variables that show up in the denominator value. This means we have to limit our domain. Remember, our domain is talking about the range of the x values. And so here, what I'm looking at is I have x minus 5 in the denominator. What happens if I happen to put a 5 in there? 5 minus 5, that's 0. I'm dividing by 0. But can I put anything else in for x? Let's find out. We've done this before, actually, but just as a reminder, you would take your denominator value, set it so that it cannot equal 0, because you cannot divide by 0, and then simplify this equation. This gives me x cannot equal 5. And just as a reminder, in interval notation, you would write this so that the domain is everything up to 5, not including it, hence you're using a parenthesis, union from 5, still not including it, up to infinity. So you're just excluding the one value, which is 5, creating a gap in your overall domain set. Let's try another one. All right, I'm going to do the third example. I lied. I'm going to do the second example because I just lost my place on the paper. Haha. Okay, so I have q plus 7 over q squared minus 3q plus 2. Okay, now, when I'm looking at this particular problem, I'm looking to see where my variable is. I see I have a q here, I have q here, and I have a q here. So I have q's in both numerator and denominator here. But what am I actually concerned with? I'm concerned with anything that makes my denominator equal to 0. So I don't really care what happens up here in the numerator value. I'm concerned with what is going to change my denominator to 0. So let's solve that. So I have q squared minus 3q plus 2 cannot equal 0. Well, hey, this is a trinomial that can be factored. So let's do that. Let's factor this down. Cannot equal 0 still. I have q, factors of 2 are 2 and 1. Signs are the same and they are both negative. Solve this out. Hey, this looks like zero product property. We just talked about that in another lecture. Let's apply that. So I have q minus 2 cannot equal 0, and I have q minus 1 cannot equal 0. Solving this out, q cannot equal either 2 or 1, so go least to greatest, 1 or 2. And in my interval notation, my domain will go from negative infinity up to 1, not including it, union the space between 1 and 2, because you have some decimal fraction values there, union from 2 to infinity. I kind of ran out of space there, so I'm going to erase this a little bit just so I can get it in there. That's an infinity symbol. There we go. And so that would be my entire domain for this problem. Now I want to point out something, just as a pattern, if you will. Notice that when I had one value that I excluded, I had one union, meaning there's a gap with this value. So one value excluded, I have one union. Here I have two values excluded, I have two unions. So this is kind of a built-in mental check as you're going through and working through the domain type of problems. If I'm excluding two values, I know I should have two gaps, so I have to have two different union values. Excellent. Now let's try another one. Just because domain is such an important practice to get into, it's an important concept. Now we're getting to that third example, because I did not lose myself on the page this time. Very good. So I have f of a, using that function notation still, is equal to 2a minus 3 over 4a minus 7. Again, I have an a in the numerator, a in the denominator, but which one am I actually concerned with here? I'm concerned with the denominator, because that's the only one that can change to potentially give me problems. So I'm going to say 4a minus 7 cannot equal 0. Solve this out. I have a cannot equal positive 7/4. So you're going to add that 7 divided by 4. Your domain value for your set is a negative infinity to a positive 7/4 still excluded, so you have a parenthesis there. Union 7/4 to a positive infinity. All right, let's try another one. So I have f of m is equal to m plus 7 over m. Again, I'm really only concerned with that denominator value. M cannot equal 0. Well, hey, that's simplified already. There's nothing else to do. So that means my domain here is negative infinity to 0, union 0 to infinity. Awesome. Now, let's do another one. This one's fun. The next two are actually really fun. So I have f of t is equal to t minus 9, there we go, divided by 5. So where is my t variable? Only in the numerator. So what if I took my denominator, just routinely here, since you see that as our practice, and I say 5 cannot equal 0. Is there anything that you can solve for here? No. 5 cannot equal 0. Well, that's a true statement. So that's pretty good. So if there's nothing that can change my denominator, because this is a constant value of 5, then that means my domain is everything, negative infinity to infinity. I have no excluded gaps. Pretty awesome. So if you're dealing with just a constant value, then you have a continuous domain. So you don't have any gaps throughout this domain. But if you have a variable in your domain, now you have something that can change. You have to test to see if anything will change it to that 0 value. Okay, very good. Let's do one more domain problem, and then we'll jump into a slightly different mode. All right, this last one, I have f of x is equal to x minus 6 over x squared plus 1. Okay, now I have an x in the numerator, x in the denominator. Let's go ahead and take that denominator, set it so that it cannot equal 0. And let's see, can you factor that particular problem? It is two terms. Technically, both of those are perfect squares, but here's a problem. It's not a difference of squares, so you can't use that definition. It's a sum of squares because you're adding these terms. Remember what I said back in our factoring unit. Sum of squares does not factor. Sum of squares does not factor. So because this does not factor, and there's nothing else that you can really do, technically your domain will be everything. Now let's say you didn't believe me. Let's say you said, all right, I'm going to subtract 1. That means I have x squared cannot equal negative 1. And I know, hey, square roots. We haven't talked about square roots just yet. We'll get to that later on in the course. But if you're one of those people who already knows about square roots, you're like, hey, square root, all right, yeah, square root of x squared is x. And then I have square root of negative 1. Oh no, that breaks down. Ugh, that's not even real. So, no, there's nothing that you can do with this problem. I suggest sticking to the factoring, but if you're one of those square root people, you could look at it that way too. So you do still just have a domain of infinity, negative infinity to infinity. All right, I'm going to get some board space as we shift into this next little subsection. Because we're talking about fractions and more details, or rational expressions. All right, let's say I have some term a over b, some fraction. If I were to look at this problem, I have two separate bases, a and b. If I were to change this problem, let's say I multiplied by c over c. So I multiplied by 1. My light just went out, so I do apologize about that. But let's say I multiply by 1. 1 being anything over itself. Then technically this is the same as like AC over BC. Okay, how does that help me? Well, in reverse, I could actually pull this 1 out and cancel it, right? Let's see how that works. Let's say I have 7k over 14. 7k over 14. Well, technically this is like 7 times k, right? And then this is like 7 times 2. 7 over 7, something over itself, is 1. So couldn't I cancel those? Sure. So if I cancel that 7 over 7 out, what am I left with? K over 2. So you're simplifying your fractions like you've been doing already. This is a very simple example showing this property, so I took it a little bit slower. But what if you have something a little bit more complex? What if you have something like this, where I have a trinomial over another trinomial? Yikes, that's insane, right? Well, let me ask you this. Taking it in pieces, can you factor just the numerator? Sure. Can you factor just the denominator? Sure. Let's go ahead and do that. Let's see what happens. So I'm going to work horizontally here. That way I can keep my numerator and denominator separated and you can see where they're going. For my numerator, I'm factoring that first. I have y and y. Factors of 3, I have 3 and 1. Signs will be opposite, and I know the greater sign goes to, the greater term gets the positive. So that's a plus and a minus. Okay. Let's look at that denominator. I have y and I have y. 2 and 1. Now, I know the signs are the same and they're both negative. Okay. So now I have two products in the numerator and two products in the denominator. Cool. Is there anything that I can cancel? Yes. I can cancel the entire term of y minus 1 because it occurs in both numerator and denominator. Now, this only works if you have something exactly over itself as a product. So something in the numerator exactly over something in the denominator, and those have to be the same exact term. I'm using exact a lot to emphasize that. What are you left with? I'm left with y plus 3 over y minus 2. That is my end result right there. Not too bad. It's the same exact principle as what we were doing here with the basic idea of a fraction and simplifying it. I have something exactly over itself. I could cancel that. And whatever I'm left with is what my simplified version would be. It's exactly what we did there. All right, let's try another problem. This next problem, let's say I have 3y plus 9 over y squared minus 9. Okay, so the numerator, can I factor it? Sure, there's a GCF there. I can pull out 3, I'm left with y plus 3. How about the denominator? Sure, it's a difference of squares. So I can technically write this out, y plus 3 times y minus 3. Can I cancel anything? Absolutely. The y plus 3 occurs in both numerator and denominator, and they are products, so I can cancel those out. And so I have 3 over y minus 3 left over. And that's it. That's the whole process of simplifying your rational expressions. Let's try another one, shall we? I have 1 plus p cubed over 1 plus p. Get my little dividing line in there. All right, well, that denominator definitely doesn't factor. It's just 1 plus p. That's as simple as it gets. What about that numerator, though? 1 plus p cubed. It's almost like it's a sum of squares. Let's look at that. So I know my denominator is 1 plus p. It's as simple as it gets. I'm just going to carry it over. My numerator, I'm saying it's a sum of squares. So I'm going to have a binomial and a trinomial. Remember, get that binomial first. That's usually the hardest part, and then you figure out the rest from there. So if you need to look up the definition, again, sum of squares. But we're going to go ahead and apply this. So what times itself 3 times would give me 1? That's 1. What times itself 3 times would give me p cubed? That's p. The sign is the same. Over here, my first term is my first term squared. My last term is my last term squared. There we go. My middle term are these two multiplied, so that's just 1p or just p. And my signs are the same, right, because it's the same as the original, opposite, and always positive. Cool. Is there anything I can cancel? Absolutely. I can cancel 1 plus p from both numerator and denominator. Now you might be saying, well, what am I left with down here? Remember, this is technically like 1 times 1 plus p as a product, technically. So technically you're left with this over 1, but anything over 1 is indeed itself. So I have 1 minus p plus p squared as my end result. But if you need to see that 1 in the denominator, absolutely you can write it, but your simplified versions should still come out to this. Okay, very good. Let's try another one. I am on example 5 at the very bottom of the page. I have 3x plus 3y plus rx plus ry over 5x plus 5y minus rx minus ry. Okay, so I've got two 4-term polynomials. Whew. Remember, check for a GCF first. I don't have one in either numerator or denominator in this case. With a 4-term polynomial, remember this is where you have to play Math Ninja. Cut it in half. Look for a GCF in the first half, look for a GCF in the second half. That is your factoring by grouping method. So I'm going to look at just this numerator first. Because this is a longer problem, I am going to work vertically just to show a difference in how I can work. So I can factor that first half, cutting it in half with a 3. I'm left with x plus y. On this side, I don't want to change my sign, so that's plus. I can factor out an r here, and I'm left with x plus y. I do have a denominator, but I'm going to come back to this because I want to finish my numerator work first. Just how I work. So I have 3 plus r, and I have x plus y. Awesome. Now let's look at that denominator. I'm going to split it in half again because it's 4 terms. I can pull out a 5 over here. I'm left with x plus y. Over here, I do want to change my sign, so I'm going to pull out a negative r, and I'm left with x plus y. So I can pull out 5 minus r, and I'm left with an x plus y. Very good. Cancel what you can. You're left with 3 plus r over 5 minus r. All right, not too bad. So as you're going through these processes, just again, take it one step at a time. Notice how my workflow in that problem looked at just the numerator and I took it all the way. Then I looked at just the denominator, took it all the way. That's a great process to work with. That way you don't lose your train of thought as you're going through. All right, let's say I have y plus 2 over y squared plus 4. So I have y plus 2 over y squared plus 4. Can I factor? Y plus 2? Absolutely not. That is as simple as that gets. But y squared plus 4, can I factor that? They are perfect squares, but this is a sum. No, I can't factor a sum of squares. So that is y squared plus 4. That is as simple as it gets, folks. So don't force a factor. Look to see if it can factor. In this case, it cannot. So leave it alone. All right, I want to go over another concept really quick, and that is the concept of -1. Now, with a fraction, you've typically seen -1 where it's just a negative and it can float bottom, top, or out to the side, and that's perfectly fine. But with an expression such as y minus 2 over 2 minus y, technically, this is -1. And you might be looking at it and saying, what are you talking about? There is not a -1 there. Believe it or not, there is. Notice how these are written in opposite pattern. They're actually quite literally opposite because this is a positive y, this one's a negative y. This is a -2, this is a positive 2. So they are quite literally opposite of each other. If I were to rewrite this so that I have the same format, I'm not going to change my numerator because I like my y first, just a preference. So I have y minus 2. I'm going to try matching this. So if I were to rearrange this, this is like a -y plus 2. I just flip them around. But I want a sign change here because I want my y positive. So I have y minus 2 still. Pull out a negative 1 and I have y minus 2. My sign changed. Well, this and this can cancel. So this is technically like 1 over negative 1, which is just negative 1. There is a negative 1 there. I didn't lie. So anytime you have the opposite values, this is also noted on your page, right up here in the little box. Anytime I have opposite values, this will come out as a definition for negative 1. Now, this is a very important concept as we move forward because it will pop up a little bit more often. Let's say I have something else. Let's say I have p minus 2 over 4 minus p squared. Interesting. So first things first, let's write our p first. I like my p's before my values. That's just a preference. So I have p minus 2. I didn't change that. This, I'm going to pull out that negative 1 automatically, and that gives me p squared minus 4. So I pulled out a negative to change my sign. I saw it was negative here, so I wanted this positive p. So I pulled out my negative, reversed my terms. I have p squared minus 4. Cool. Can I factor? Yes. So I have p minus 2, nothing's changed in the numerator. I have that negative 1 times, I'm factoring. I was rewriting my problem. I'm factoring my p squared minus 4. That's p plus 2, p minus 2. I can cancel p minus 2 out. I'm left with 1 over my negative. That is not a 6. I don't know what I was just writing there. P plus 2. There we go. So I have 1 over negative p plus 2. Alternatively, remember you can write this as a negative 1 over p plus 2, or you could write it as a negative 1 over p plus 2 like this. All three of these are saying the same exact thing. Okay. So, let's jump into multiplying and dividing. I'm going to get some board space, that way we're nice and situated for this next part. This is kind of jumping into that 7.2 section now. All right, let's say I have 2r plus 4 divided by 5r times 3r over 5r plus 10. And I get a simple instruction, something like factor, multiply, and simplify. Sure. All right, so what am I looking at here? I've got two fractions, right? They are in a product with each other. So remember, whenever you're multiplying fractions, technically you're going numerator to numerator, denominator to denominator. But here's my question. Can I factor this anywhere? Yes, here I have a GCF of 2. I'm going to work vertically so we can see it. So here I have a GCF of 2. So I have 2r plus 2. Nothing that can happen here, so I got 5r. Over here, I have still my multiplication, 3r over, I can pull out a 5 here, so that's 5r plus 2. Now, remember, the definition of 1 is something over itself, right? When I'm multiplying my fractions, technically I'm multiplying numerator to numerator, denominator to denominator. So basically I'm combining these like that, right? So it's like one big fraction. Is there anything I can cancel? Certainly. R plus 2 probably stands out for you. What about this R? Sure. Anything else? doesn't look like it. So I have 2 times 3, which is 6. 5 times 5, which is 25. And that's it. Nothing else can simplify there. If it could have simplified, we would have already done it. All right, let's try another one. So whenever you're going through this process of multiplying rational expressions, you're really factoring it down and then seeing if there's anything you can cancel. That's essentially it. All right, there's a lot of C's here, so don't get lost in it. But see if you can factor step by step. Over here, I can pull out a C. I'm left with C plus 2 over. This can factor, certainly. That is C plus 2, C minus 2. Over here, numerator, looks like a trinomial I could factor into C minus 2, C minus 2. How do I know? Well, 2 and 2 gives me 4. Signs will be the same. They're both opposite. Over here, I can factor out a GCF, which is C. I'm left with C minus 1. Is there anything I can cancel? Remember, this is a product going across. So yeah, I can cancel. I can cancel that C plus 2. I can cancel C minus 2. I can cancel just the C. What am I left with? I'm left with C minus 2 from here over C minus 1. And that is it. All right, so multiplying your rational expressions seems pretty easy. Seems very easy, in fact. But, you know, multiplying, you just have to really break it down, factor every single little piece that you can, and look to see if there's anything that you can cancel. How is that different from dividing, though? So what we're going to do is we're going to jump into dividing our rational expressions. And what I'm going to show you is a really cool little technique. So let's say I have 5p plus 2 over 6 divided by 15p plus 6 over 5. Now, here's the thing. The first step that we had with multiplying was to start factoring, break everything apart, get lots of little working pieces, then cancel. The first step with dividing is actually not that. The first step that we're going to do is something called keep, change, flip. We keep the original exactly as it is. We change the sign from division to multiplication, and we flip or reciprocate the second rational expression. So we keep, change, flip, and that's what we get here. We went from division to multiplication. Now what do? At this point, you break it up into little pieces and see what you can cancel. So we're going to factor. There's nothing to factor here. Nothing to really factor with 6. I usually don't factor out my constant values, just as an FYI. So I have 5p plus 2 over 6 still. Over here, I have 5, not factoring, but this part can factor. So this part I can pull out a 3, and I am left with 5p plus 2. Can I cancel anything? Absolutely. Cancel that 5p plus 2. I'm left with 5 over 18, because you have 6 times 3 there. And that's it. That is all there is. I've given you the secrets to the universe, at least for section 7.2. So let's do one more. And we're going going to take it in steps. So I have y squared minus 2y minus 3 over y squared plus 4y plus 4 dividing by y squared minus 1 over y squared plus y minus 2. A lot of little pieces there. I'm making sure I wrote it completely. Okay, very good. Now, at this point, what is my first step? Well, I'm dividing, so I want to actually change it to multiplication. So I need to use keep, change, flip. So keep, change, and flip. So that's what we're going to do. So I have y squared minus 2y minus 3 over y squared plus 4y plus 4 times this side I have y squared plus y minus 2 over y squared minus 1. Okay, very good. So I did my keep, change, flip. I'm now back to a multiplication style problem. I am now going to factor. So let's factor everything that I can. For my numerator on this side, y and y, 3 and 1, signs are opposite and the greater is negative. For my denominator on this first rational expression, y and y, factors of 4, 2, and 2 that I want to use. Signs are the same. They're both positive. Multiplying over here. Numerator, break it down. I have y and y, 2 and 1. Signs are opposite. The greater is positive. And then I have a difference of squares down here. Y plus 1, y minus 1. Whew, there's a lot of working parts there. So what we need to do is we need to see if there's anything that we can cancel. So I see I have a y plus 1, so I can cancel that out. I see I have a y plus 2, so I can cancel that out. I have y minus 1, so I can cancel that out. And I am left with y minus 3 over y plus 2. And that is it. Okay, guys, so for this section, what you need to do is, we covered a lot of content, but what you're going to do for any of these multiplication or division problems is take it step by step. If you're dividing, first step is keep, change, flip. After that, you're in a multiplication style problem. That's where you want to factor, break it down, and then you want to cancel anything that you can. When you cancel, it is extremely important that you cancel exact terms. So it has to be the same exact expression that you're canceling with the same exact expression, numerator and denominator. That's it. All right, thank you guys. I'll have another section coming up for you in just a moment.